All right. Hello and welcome back to Games with Go, where we are learning to program by making a series of games in the Go programming language. I am still on the road this week, so I apologize for the reduced microphone quality. I'll be back on my home PC Thursday. All right, so last episode we made a linked list in order to implement a very basic linear story where we can go from page to page. Today we're going to kind of refine and clean that up a bit and learn some new Go language features. And then at the end we'll start on implementing a branching story where the player can actually play and it'll get more interesting. All right, so first thing I'm going to introduce is a new Go language feature, which has to do with creating methods. So if you're familiar with Java, C++, or C# or other object-oriented languages, you might be used to the idea of being able to have functions inside your classes or your structs. So you might be able to have something like, instead of play story defined outside of the struct, you could have it right here. And then when you define things that way, it associates your function with this type, right? It means that play story goes along with story page. And then there's usually a syntax like this, where you can have your page and hit dot and call play story that way. So Go lets you do something similar, but it works a little bit different. You don't actually put functions inside of your struct like that. What you can do is functions can have a receiver type. And what that means is you can put a type in front of your function name, like this. And you give it a name and a type. And then you will have page available to you here. And you can use it just like before. But now instead of calling play story and passing in a page, you would have a page and call play story from it. Like that. Now there's not really any real difference behind the scenes with how this works. You could do it one way or the other. It's the same. It's merely sort of a convenience. It can make it more clear that the play story function is something that operates on your linked list nodes, or our story page nodes in this case. Another thing that's nice about it is if you have an editor that has like IntelliSense or autocompletion, when you type out something like this and hit period, it'll show you the functions that are available. So you can see that play story is here. So if you're building out, if you have a type or a struct you've made with a whole lot of operations that are going to be on it, it can be really nice to do them all this way, so that people that are, if someone else is using your struct later, they can hit period and kind of see all the things that are available. So it's just a way to make your data structures nicer to use if you use this receiver syntax. And it should be noted that you can do this not just for types that you define, but the primitive types as well. So you could make up some function like this, and then you could then call this function from integers. You could do things like 5.square, and that'll work. That's kind of cool. All right, if you've got questions at any point, just type them into chat. I'll be checking in periodically. Oh, cool. Someone, Texas Nipsey, has shared one of his homework solutions. All right, this is cool. So he's got an add page and a delete page. Cool. Okay, this is good. So I'm going to potentially show you a trick to make delete a lot simpler. Although I can see you've got the right idea here that you need to pass in a double pointer. So that is very cool. Good job. So I might talk more about delete at the end here. So there's some ways to simplify this. Cool. So yes, Text Nipsey is saying in chat that doubly linked lists seem like the best way to go. This is a singly linked list, and we can kind of visualize that with a diagram. If you're new to computer science or programming, it can help to visualize things this way. And I only have MS Paint with me today. I don't have my little drawing pad, so it'll be a little slow and awkward. So these circles represent pages or linked list nodes. And then we can represent the pointers from one node to another with little arrows. Let me just draw these. Right, like that. So you can think of this as page 1, page 2, page 3. And it's these are a one-way link. Each page knows where its next page is, but a page does not know what its previous page is. But it's absolutely possible to also have a doubly linked list where each node also has a pointer to the previous node, like that. And so what that would look like in code is each node would also have a previous page pointing to a story page. And sometimes that can be very, very useful. Check in with chat again. Cool. Okay, so the other thing I wanted to talk about was the use of recursion. So we implemented our function that steps through each node of the story or each page of the story by using recursion. And that's a fine way to do it. One thing to keep in mind is when you do that, you've got your function calling a function, calling a function, calling a function for however many pages in the story there are. So if the story had 100 pages, you would end up with a 100 deep call stack. So you've got like 100 instances of the function running at the same time. And the way that works behind the scenes, let me just clear this out. You can think of memory as being this big chunk. And at the bottom, you can think of it as the bottom, logically, is something called the stack. And the stack is used to as a place for things to go when functions are called, right? So when a function is called, there's variables inside the function. You need to store what those variables are somewhere. And, and that can go in the stack. And every time you call a function, you need to store a little bit of data in the stack. And so in the case of this, if we call play story, there's going to be a little bit of data stored here. And when play story calls itself again, the stack has to grow. It just grows upward to store the next instance of play story's data. And it gets called again, and the stack will grow. And then when the function returns, finally, if you finally get to the end, the stack just shrinks back down. So you can just think of it as erasing. Let's do it bigger. Right, so when a function returns, the stack shrinks back down. So depending on the language or operating system you're using, the stack might have a limited size. So one danger is if you have too many functions or a function that calls itself too many times, the stack gets bigger and bigger and the program blows up. In Go actually does some fancy stuff and can make the stack pretty much as big as you want. So you're not in danger of that, but it still could waste a lot of memory if the stack just keeps growing and growing. So many compilers for many languages, when they see a recursive function like this, where the last thing you do in the function is the recursive step, is they can automatically convert this into a loop. And that's called tail call elimination, because it's referring to the fact that the tail of the function is the part that's recursive, and the compiler can automatically turn this into a loop. And once it's a loop, you no longer have the stack growing. You just have a single loop, so it's more efficient and uses less memory. The standard Go compiler does not do tail call elimination, and they do that because they want debugging to be easier. That way, if you have an error when you're 5 calls deep in deploying the story, for instance, you can see that in the debugger, whereas if the tail call was eliminated, you can't. So the bad news is you don't get tail call elimination with the standard Go compiler. The good news is you get better debugging, and in Go the stack can grow dynamically, so you can go a lot deeper into recursive calls without blowing up, which is nice. Now, whether you should do something recursively or do it more efficiently with the loop just depends on what's going on. If we expected to have stories with millions of pages of long, we definitely want to make this a loop. You also have to consider how much simpler the solution is done recursively versus a loop. Now in this case, a loop is really not any more complicated than doing it recursively. So in my opinion, but people disagree on this, if the non-recursive solution is just about as simple as the recursive one, I think it is generally better to do a non-recursive solution. That way you don't depend on the compiler making it efficient for you. It'll just always be efficient on any compiler. So let's just do that real quick as an exercise. Let's change this and make it use a loop. So it's pretty simple in this case. We're going to use a loop. And remember, the only kind of loop there is in Go is a for loop. And basically, we just want to keep going. As long as page is not equal to a nil pointer, we can print that page. And then advance page to the next one. So we can say page equals page dot next page. Okay. So let's give that a try. Let's try playing from page 1. And see how it goes. All right. So that works fine. So you can see that this solution isn't any bigger. It's not more lines of code. It's not hard to understand. So I feel in cases like that, it's better just to go with a non-recursive solution, because then you can always count on it being correct. But in cases where it feels simpler to use the recursive solution, and we'll see one of those soon, it can often be much better to leave it that way, especially if it's not going to be a serious performance impediment. All right, just checking on questions. No questions right now. Okay, some terminology stuff. So you may have heard me refer to this type of call as a method. So you'll hear 3 different terms, pretty common in programming. You'll hear about functions, procedures, and methods. And people will use these interchangeably and incorrectly all the time. I do too. There are some proper definitions which are just good to know. So a function has a return value. And you'll notice in Go you can create functions that don't return something, and it's still called a function in Go. Technically, if a function has no return value, if all it does is execute other commands that are just side effects, you call it a procedure. So has no return value, just executes commands. Now in normal programming, functions also execute commands, but they have return values. And then methods are referring to functions that are attached to a struct or object, etc. So when you have a function attached to something like this, that's a method. A function that has a return value is a function, and a function that has no return value is sometimes called a procedure. I think it's perfectly fine to just call all of these things functions, but it's good to know this terminology because other people will use it that way. Jaja123 in chat is asking if there's somewhere that I can donate. Yes, you can go to the website gameswithgo.org and you can contribute. And by donating, you get access to the source code. There's a GitHub repository that you'll get added to. And every night I push the new stuff up there. All right, so this way we're building up the story is kind of cumbersome, right? We're having to create these pages and we start them out with a nil pointer first, and then we set the nil pointer. It's a lot of typing, it's error prone. What if we leave one of these things nil? That could cause an error. So let's add some more functions to our linked list so we can build up stories more easily. So let's clear this out again. Let's just draw a new linked list and we can talk about how we can add things to the linked list. I apologize for my terrible touchpad drawing skills. Okay, so let's say we had a linked list like this with 3 nodes, and we wanted to add a new node to the end of it. Okay, so we're going to have a pointer to the head of our list, and we want to add a new node to the end. So all you have to do that is walk down to the end of your linked list, and this last one's going to have a nil pointer for next page. So all we got to do is walk down to the end of the list until we find one that has a nil pointer for next, and change that nil pointer to point to our new node. Right? So that's a very simple operation. So let's do that. Let's make a function. We're going to associate it with the story page struct, and that's called a receiver type in Golang. That's the terminology they use. And then we'll call it add to end. And add to end is also going to take a page to be added. And then we need to walk down the linked list until we find a nil pointer for next page. So while the page.nextPage is not equal to nil, page equals page.nextPage. So this loop's going to keep advancing down the linked list, misspelled nil, until it finds one where next page is equal to nil. And we don't need parens like C. Okay. So once this loop is done, we know that we're at the end of the list. And so all we have to do is take that end node and set next page equal to the page to add. All right, and I think that should be it. And let's make this even simpler. What we can do, instead of taking a story page node, let's actually just take a string. And then what we'll do is we'll make the story page node in here. So page to add is equal to text, comma nil. Okay, so here we're going to construct a story page node that's got the text that we passed in and a nil pointer for next page, because we know that this page we're going to add is going to be the new end of the list. So it's not going to have, it's not going to be pointing to anything at the end. And this needs to be a pointer, so we need the address. We need the ampersand there to get the address of that story page. And now what that lets us do is instead of having to do all of this, we can just say page 1 dot add to end and just pass the text that we want for the next page to be added. We don't have to worry about nil. Do it again. And then we don't have to do this fixing up of the next page pointers either. Okay, let's give that a try. Great, it still works. And now it's a lot less code to be able to build up a story. And you can imagine if we were loading up a story from a file, like if we let someone write the story in a JSON format or something, or just plain text, it'd be a lot easier to write that function too. So we can just use this add to end to keep building up the story. Someone asks in chat, why not just get the address of the story page when you assign it to page.nextPage instead of declaring it as a pointer? So what they're saying is up here, you could go like this, and then get the address there. That is perfectly fine too. I don't know that there's any difference at all. So kind of whatever you prefer. It's likely that when you compile it, it's ending up the same machine code either way, but I'm not sure of that. Since we're only using it as a pointer, it's possible that this is more clear, but either way is fine. Yeah, and chat also mentions you could do it this way. And that might actually be preferable because now we've reduced the lines of code. And reducing the lines of code is usually a good thing, as long as you haven't introduced any other complication. So good idea, chat. Thank you. All right. Another useful function we might want is suppose we wanted to let users of the program, add their own pages into the middle of the story. We might also want to have an ability to add nodes into the middle, not just the end. So what that would look like, go back to our linked list here. We might want to add a new node, say in between nodes 2 and 3. All right, so say we've got this new node, and we want to add it in between these. So in order to do that, all we need to do is erase that next pointer and have it go to our new node. And then have our new node point to the old next pointer that we just erased. So you're just kind of wiring it up. And this is one of the benefits of linked lists, is that you can add a new node like this in just a single step. No matter how big the list is, the list can be a million things. If you add a node and you want to insert a new one in, it just takes one step. And if you remember from the guessing game, we talked about big O notation. We talked about how the naive approach to the number guessing game was O of n in terms of runtime. That means if the search space for numbers was n numbers big, you would have to search through n possibilities. And then when we use the optimum technique for searching, where we kept splitting the search space in half, that dropped it down to O of log n, which is much, much better. So adding an element to a linked list like this is O of 1, or it's called constant time, because no matter how big The linked list is the number of steps to add an element or insert an element like that doesn't change. So that's very, very fast. And if you have an algorithm or a project you're working on where the vast majority of things you're doing are inserting or deleting elements from a collection, a linked list might be what you want to turn to. If you're not adding or inserting things that often, a linked list can be slow, and we'll talk about why later, but that gets into some details of hardware. All right, so let's try and do our adding in the middle function. So again, we're going to do a method on story page. And we'll call this add after, because what we're going to do is add the node that we pass in after the node we're calling on. Okay, so probably the first thing we want to do is set the new node. Let's do this with a string again, so you can just pass in a string. And we will make a new page out of it. And we know already that the new node is going to point to the current node's next page. I used the wrong syntax there. Okay, so when we set up the new node, we're wiring up this pointer right here. And then page.nextPage is going to equal new page. So that second line does this step here, where we rewire this node from going to there to our new node. And that should be it. So we can test this. Try adding a new node just after. Do a little test case and play our story. Let's see what happens. All right, case sensitive. Cool. So we see that this got added right after the page one node. So that is working well. All right, so delete. So delete's kind of tricky. With a singly linked list, or perhaps a doubly linked list too. I'm debating whether I want to get into delete or not, because it's pretty complicated. I think we'll save it for later. Are there any questions so far about adding to the end of the linked list or inserting into the middle? Okay. So we're going to come back to delete. I think once everyone's a little more comfortable with pointers and stuff, we'll come back to it. There's a cool trick to make it simple in terms of how many lines of code it is, but you kind of have to wrap your head around pointers really well to understand what's going on. It's hard for even me. All right. Let's make this more interesting. instead of having a linear story, let's set up a new project that can do a branching story. So I'm going to make a new folder, branching story, then a new file, branchingstory.go. Still be package main. And we'll have a func main. And we're going to import format for sure. Oh, the Go tool like looks at what your code's doing and sets up your imports for you. So when I saved it, it got rid of it because I wasn't using it. All right, so we're going to still keep things as simple as possible. So we're going to have a text adventure that can be branching. We're going to start out just with there only being 2 branches. So in every scenario in the story, you can choose yes or no, and something different will happen depending on whether you picked yes or no. So we can represent that in a similar way. We'll call it maybe story node this time instead of page, because it's more than just a bit of text. So we'll still have some text like before. And then we can have a yes path, which is a pointer to a story node, and a no path, which is a pointer to a story node. So what this data structure will let us do is instead of a linked list that you just, go one way, we'll now have something that looks like this. So each point in the story has multiple ways it can go. We can go yes, we can go no, we can go yes or no again. And then some of these points we could make them winning paths, and others could be dead ends where you lose. And we can build up what we call in programming a tree. So this is a binary tree because there's only 2 choices at each point. And these can get as big as you want. So let's start out setting something up. So let's make a new story node. And programmers tend to call the first node in a tree the root, which doesn't always make sense because we draw it with the root at the top. But that is life. That's what we do. So root equals story node. I don't know. What's our story? We'll be at the entrance to a cave. Right, and for now we're just going to leave our yes path and no path nil. So let's just use a really simple story that we can use for testing. So we'll have winning. We'll have losing. And then since each story node has to have a yes or no answer, we need to kind of ask a question. We need to ask the player what they want to do. So we'll say, do you want to go in the cave? All right. And then we'll say that root dot yes path. Let's say if we go in the cave, we're gonna die. So if they say yes, they're gonna die. And if they say no, they're going to win. All right. So now how are we going to actually write a function to play this game? We've got it set up. Now we got to play it. So let's try it. We'll use a receiver type of story node. And we'll call it play. So first thing we want to do for sure is we want to print out the current state of things. Print out the text. And then we need to get input from the user. So if you remember from our guess the number program, right, we can set up a scanner to read input from standard in. Scanner.scan will scan it. And then the user's answer will equal scanner.text. So what we want to do here is we want to kind of see, if the user typed yes, we're going to do one thing. If they typed no, we want to do another thing. And if they didn't type yes or no, we want to handle that robustly, right? We don't just want to crash, so we want to handle it intelligently. So what we can actually do is we can use a for loop like this. Okay, so what we're doing here, it's a little complicated, there might be some new stuff for some of you, is we're doing a for loop, and each time through the loop, we're going to set the answer equal to scanner.text. That gets the input from the user. Oh, you know what? We need to scan too. So I think we'll just do it like this. We will just use an infinite loop. And we'll say if answer equals yes, I'm going to do one thing. Else if answer equals no, do something else. And then otherwise we don't really need to do anything, but what we can do is let the user know they made a mistake. And then since we're in a loop, this will just go right back up. And in the case of yes or no, we don't want to keep looping, so we can use break to break out of the loop. Now, if they answered yes, we can use recursion here. We can take our node, yes path, and then play that, because the user said yes. And if they said no, take our node, take the no path, and play that. Let's see. case sensitivity needs to be lowercase. Okay, so let's give this a try. We'll start playing from the root. Let me check chat real quick. So someone is asking if I think if we could do a switch statement here instead of if then else. And yes, I'll introduce switch statements soon. They especially get handy if you have like 5 or 6 cases in your if then else statement. They're also a little bit weird in Go in that the break statement here would break out of the switch statement instead of the loop, which is usually inconvenient, but we'll introduce switch statements soon. All right, so I'm still in the linear story. Let's go to the branching. All right, we're at the entrance to a dark cave. Do you want to go in the cave? Let's test our bad input. That answer is not an option. Please say yes or no. So it'll just keep looping forever if we give it bad input. And let's say yes, we want to go in. Oh no, we've lost. Now, one problem you see here is we've lost, but the game is still going. So let's address that. So the problem here is we need to see if there is any more to the story or not. So after we print the current node, we can check. We can say, does this node have any more nodes attached to it? So we're going to wrap all this stuff in this if statement. So this checks to see if the yes path and no path have anything set. If not, then we know we have to be at the end of the game, one way or the other, whether we've won or lost. And then the program can return and stop executing. So let's give that a try. Okay, test our bad input. That's still good. Let's go in the cave. And we have lost, and the program exits. Let's see if we can win. All right, we won, and the program exits. Now, I think some of you, if you're totally new to programming, you may have never seen this syntax before. The and, that is basically Go's way of saying and. And you'll see that in C, C#, I think Java as well. Not all languages use that syntax, but that's what Go uses. And the reason why it's 2 ands is this means something different, which we'll get to later. If you wanted to use or, it's 2 pipes, like that. And this just checks to see if the yes path is not equal to nil and the node path is not equal to nil. So if both are not equal to nil, we keep playing the game. We get input from the user and keep playing the game. Otherwise, we exit. Any questions so far? Okay, so what are some cool things about this? So this is a binary tree, like I mentioned here. Now, if you remember in our Guess the Number game, we talked about how you can find the answer in O of log n steps, right? If you've got n numbers you got to search, you only have to try log n numbers. So as well as being useful for something like a branching story, as long as it's only 2 branches, binary trees can also give you an equivalent type of thing as the binary search we did in the number guessing game. So if you happen to build up a binary tree that had numbers in it in order, so if this was like 5, 3, 4, 1, 6. This is what you would call an in-order tree. These numbers are sorted. So let me tell you what I mean. When you add the first number to a tree, it just goes on the root. So if we added a 5 to the tree, it would go right there. If we then added a 3 to the tree, you pick a rule. You say that any number less than 5 goes to the left. Any number more than 5 goes to the right. So, this isn't correct. That wouldn't be there. No, it would. Yeah, that's good. Okay, so 3 goes to the left. If you then added a 6 to the tree, 6 is bigger than 5, so it goes to the right. If you then added a 4 to the tree, it would go to the left because it's less. Now you're at the 3. The 4 is greater than the 3, so the 4 goes to the right. And the 1 is less than the 3, so it goes to the left if you were to add that. So what this lets you do, if you need to find a particular number in a big tree full of numbers, you always know which way to go, right? Just like in the binary search, you would jump halfway to the left if your guess was too high. If you're looking for the number 1 here, well, you know 1 is less than 5, so you only need to search the left half of the tree. You don't have to search the right half of the tree. And again, 1 is less than 3, so you don't have to search the right half of this subtree. You only have to search the left half. And so you can get down to whatever number you need, guaranteed if the tree is balanced in log n steps. Now it is possible if you built a tree and did not work to keep it balanced that your tree could just be a straight line, and then it's no good. So that's something you need to keep in mind. And this is kind of equivalent to a binary search. If you have a tree that's ordered, it's like doing a binary search on a sorted list. Equivalent idea. Now that concept is not going to be too useful in this game, although maybe you could make it useful. You could maybe make your game have like distances on different paths, and you could like find the shortest distance and stuff. I'm not sure. But something useful we can do, we're going to do some recursion again. Now you can imagine if you built up a really big story, it might be useful to like print out all of the nodes in the story in some way, so you can kind of see everything, see what you're building. So let's make a function that's going to print the whole tree. So let's make a new function. It's going to operate on story nodes. That'll be our receiver type. Now what we need to do is we need to print every single node in the story. And there's a few different ways we could do it. We could first print the current node, and then print the left and right node. Right, we could do something like that. Or we could do it like this, which would print the left path passed first, then this, then the no path. Now doing it this way, if we were like storing something like numbers that were in order like this, would print these numbers in sorted order. Because we'd always be going to the left-hand side first, continually down the left side till we get to the very smallest number here, 1, and then it would print 1. And then it would go up and print numbers in order. But for the purposes of our story, we probably don't want to do that. We probably want to print things kind of as we go down the tree. So this would probably be better. So let's give this a try. So we're not going to play right now. We're just going to print the story out. And we have an error. Oh, okay. So we did not check for null or nil. So what we need to do is, well, one way we can do it. If node.yesPath is not equal to nil, then print the story. And if node.noPath is not equal to nil, then print the story. So what happened there is go try to print the node text on a nil pointer. So it doesn't exist, so it crashed. All right, so we are successfully printing all the nodes in our story. So we see all 3 that we created. But what we'd like to do is kind of represent the tree structure of our story in some way. And so one way we could do that is to indent the text as we get deeper into the tree. So one way we could do that is keep track of the depth as we go into the story. So a way we could do that is accept an integer in here. And then when we print the text, we could first sort of pad it. So what's a good way to do that? Can we do a format.print? Yes. So let's try this. We're going to do a very naive way of doing it, but it'll be fine. So for I is equal to 0, I is less than depth, I plus plus. We'll actually do depth times 2. We'll make an indentation of 2 characters. We'll just print, actually we can do it like this. We'll print 2 spaces for each level of depth that we're at. And then we'll print the node text, and then we'll just print a new line. Okay, so all this is doing is just printing out spaces based on how deep we are in the story, then printing out the node text, then doing a new line. Now what we need to do is we need to pass a depth when we do the recursion. So we just need to add 1. And that way each time we go deeper into the tree, we're going to add 1 to depth, and we'll get more indentation. So let's give it a try. Oh, we forgot when we start things off, we still need a depth, so we'll start it out as 0. All right, and now we see that we get indentation here as we get deeper into the tree. And you can imagine if you had a really complex story with lots of nodes, that would be really helpful in being able to see at a glance what all is going on. All right, so that's the first case of us kind of passing some state down into our recursion as we go. And that kind of pattern can be useful a lot. All right, that's going to be it for today, but I will stick around for a few minutes for questions if anyone has questions or comments. What we'll be doing next time is we're going to actually kind of get to a real text adventure where there can be any number of choices that you want to do. And that's really cool because once you get to that point, you can kind of build any kind of text adventure you want, anything you imagine. You can create mazes, or you can recreate the game Zork. If you're not familiar with the game Zork, you can look it up. There's various free ways to play it or download it. There's web versions you can play. It was one of the early text adventures. Pretty fun game, even though it's all text. All right, chat is asking when we're going to move on to the graphical part. So the next thing we're going to work on is the sort of complete text adventure. And that'll probably take 2 episodes, I think, to get through, maybe 3. So we're going to do things like being able to load stories from a file. And when we get to the graphical stuff, we're going to start out with SDL2 and kind of do things from scratch, like drawing the pixels ourselves. We'll do things like fractals and procedural generation. That'll probably last for a while. We'll make some games using just SDL2 and 2-dimensional software rendering. And then after that, we'll use OpenGL to do some 3D stuff. All right, everybody, that's it for tonight. Thanks for tuning in, and I'll see you later.